For the next workshop, we have a duo of presenters who will show you how to build a cloud-native data lake using open source technologies. You will learn how to deploy a sophisticated data lake solution founded on Kubernetes and build a prototype platform that can run on your laptop. Rob is a product manager at Canonical, and Enrico Deusebio is the engineering manager in Canonical's data platform team. Enrico and Rob have a combined experience taking dozens of commercial web properties and data hubs across industries to market. Let's hear what they have to share.
So, welcome to this talk. It's called How to Build a Cloud-Native Data Lake with Open Source. To set the context, go to the next slide, please, Enrico. I think it's important to agree what a data lake is, right? So, a data lake is a service, large-scale service, designed to ingest and process data from all different kinds. So relational data from databases, semi-structured machine data, for example, XML files or JSON files, and totally unstructured data too, like recordings, audio recordings, video recordings, and things like that. So the purpose of a data lake is both to have a central aggregated place to store this stuff and cross-reference across it, and for the outcomes of providing accurate reporting and business intelligence analytics for the business, or for doing more deep dive analytics with data scientists, perhaps geospatial analytics, something like that, or graph relational discovery, and lastly, for machine learning and AI. So having a large-scale repository of all of this kind of data can make an excellent foundation for your AI initiatives. So the benefits of building a cloud-native data lake are, so when we talk about cloud-native, we're talking about running things in a way that's designed to be cloud-ready from the very start. So typically that means running using Kubernetes. So in this case, it's no exception. And again, we're talking about running a data lake, running it on Kubernetes as the foundation to it. So some of the benefits here are consistency and workload consolidation. So consistency of operations, so the same way to operate your applications, be they not a data lake or a data lake. And also workload consolidation in the sense that you can combine different workloads onto the same environment, be it databases and data lakes, and other applications that you may have. You can also future-proof your investment because you have available skills typically on cloud-native stuff that may not have on other technologies so much these days. A lot of the marketplace is really oriented towards cloud technologies, and people are just a lot more familiar with it. And that also leads into long-term supportability of the solution. Another benefit is around disaggregation. So a cloud-native data lake, typically you're having the storage tier separate from the compute tier, so disaggregated, which means that you can, spin down computers when they're not in use, servers when they're not being used during quiet times, and save costs. You can also run on cost-optimized storage as opposed to local storage. So local storage generally is more expensive than using a kind of consolidated storage system. Next slide, please. So there are some more benefits. If you're running on-premise, it's very easy to integrate GPUs, InfiniBand, and RDMA, remote direct memory access, if you have that technology available. Because of the kind of cloud-native nature of the solution, it's just more straightforward. So then, from a cost perspective, having the solution disaggregated means that you have a lower cost of scale. The solution is more scalable because both of the two planes, the storage tier and the compute tier, can be scaled independently. And then lastly, your cost should be more predictable. You should be able to calculate the cost of the solution long term in a predictable manner, in a more predictable manner than you might with other technologies and strategies. Lastly, there's something around sovereignty to be said. With a cloud-native data lake, you're not necessarily tied to a given service provider, whether that's a data center provider or a cloud service provider, a public cloud service provider. So you can move your solution from cloud to cloud or from data center to data center should you so wish. Another consideration here is egress fees from some of the cloud service providers, which you can circumvent if you have a solution that's cloud native, but not necessarily running on a public cloud. And then lastly, you can build an environment, in this case, most likely on premise, for very sensitive workloads that you wouldn't necessarily want to put in a public cloud. So I'm going to talk a little bit about the architecture of such a solution now. A cloud native data lakehouse architecture. So when we're talking about a data lakehouse, we're talking about a data warehouse on a data lake. So hence the name lakehouse. So this is how it kind of looks in kind of abstract terms. So you have a disaggregated object storage system as a foundation that stores the data. So it's going to store your relational data, your semi-structured data, and your unstructured data in one storage system. You then have a distributed parallel data processing tier, which is going to process your data from your data disaggregated object storage system by distributing tasks across a bunch of systems, servers, and processing in parallel. So taking slices of the data or partitions of the data set, assigning each partition to a given node in the cluster, compute cluster, and then processing in a coordinated way. The benefit of doing this is that it goes a lot faster for large data sets. And lastly, we have at the top tier analytics tooling for data scientists and other users to do analytics, write analytics applications that process the data using the aforementioned distributed parallel processing cluster, and a query engine. So this is a way to integrate external tools, for example, BI applications like Power BI or ClickView, Tableau Server, or Apache Superset. So the technologies look like this if we map them. It doesn't have to be these technologies. These are the technologies that we're going to talk about in depth today. So at the disaggregated object storage tier, we have like AWS S3 or Azure Storage or an equivalent. So it doesn't have to be those cloud storage providers. It could be something like Ceph or MinIO or something else that has an S3 API. Apache Spark is nowadays de facto big data processing engine. In this case, it's running on Kubernetes. I mentioned that there's a cloud native play, and therefore, typically we're talking about Kubernetes, not only, but not exclusively, but usually that refers to Kubernetes. So in this case, Kubernetes is acting as the cluster resource manager on behalf of the Spark application. So it's coordinating the launch and execution of Spark jobs. At the top tier, the analytics tooling, we've got Jupyter. So Jupyter is a kind of IDE, as it were, for developing integrated development environment for developing analytics. It's very popular with data scientists, perhaps the most popular tool out there for this purpose. And QB is a query engine for Spark queries. So it will allow you to expose SQL, structured query language, which is the language of databases, but then translate that into big data applications that run at very large scale. You can connect to it using JDBC and ODBC, which are the standard database connector architectures, industry standard connectors. Yes. Next slide, please. This is a deep dive on Spark itself. So I mentioned that Spark is the industry standard big data processing technology nowadays. So Spark contains several libraries of functionality that make it extremely useful, and that's why it's so popular. So one is Spark SQL, which allows you to process data using structured query language, the standard language of databases. And then you have Spark MLlib, which is a collection of very popular machine learning algorithms. So it's not deep learning necessarily, but all of the other machine learning that is so important these days. GraphX is a network analysis library. It allows you to build, social network analysis and things like that, which is important in many kinds of business. And then Spark Streaming is a library for kind of a continuous processing of evented data. So as data moves through a stream, you can process it. You can use window functions to process the last perhaps 5 minutes of data, or just continuously process data and send it from A to B in a transformed way, or perhaps do analysis in the meantime on that data. So the architecture itself, sorry, if you go back a slide, please, Enrico. So the architecture itself of Spark is that it has a driver application, which is kind of the coordinator of the job that you've written, and that driver application will coordinate and assign work to executors. Executors then run tasks. They can run many tasks. Each task is a unit of work in a Spark job. So each task will typically take up a slice of data and do something with it. And that's more or less the architecture. It does have some caching capabilities as well in order to accelerate its performance. Now we can move to the next slide. So QB is, as mentioned, it's a service that runs on your Kubernetes cluster that allows you to expose Spark SQL, so SQL queries, to external components. So here we see open database connectivity, so any ODBC compliant tool can connect to it. JDBC, which is for Java, the same. So it's Java database connectivity. And then, with those two, you can connect things like Tableau Server, Apache Superset, typical Spotfire, or whatever you might have to your Spark cluster via QB. So QB itself has, it has high availability built into it. It has load balancing as well. So it does this by distributing like a farm of QB servers, which distribute the load across them from your applications, your dependent applications. It can also be multi-tenant, so that you can have multiple user groups querying data in an isolated manner. Excuse me. And lastly, it has like what's called a meta store, which contains the data catalog about the data being processed. So like in table format, so SQL tables, which tables are held in which data files on the cluster, and statistics about them so that the jobs go faster. That data is typically held in a database, for example, Postgres. Can be held in a Hive metastore or a MySQL database as well. So I don't know if there's anything else we haven't discussed already on that slide, so we can move on. Yeah.
Okay, so what we wanted to do today was, with the premise of Rob, to actually go ahead and actually set up and demo how to build a data lakehouse using these open source projects. So a data lakehouse which is able to basically ingest streaming data using Kafka, and then to process this data using near real time, using Spark Streaming, to then consolidate the results into an object storage, an S3 object storage, and use Postgres, as also Rob mentioned, to store the data catalog. So all the information about how the data is structured, divided in databases, in tables, as well as the schema of the data, to then finally expose the results using QB that Rob just discussed. So first of all, we are going to set up the environment. So all this data lake will be deployed on top of MicroK8. So MicroK8 is actually an extremely lightweight and simple, yet production rate Kubernetes distribution. And as you can see, you can just install this in your local system with just a few commands that you can install it and then configure it. And with just these few commands, you would have a MicroK8, actually a K8 cluster running on your local machine. We're then using Mini.io for storing data. So Mini.io is actually an object storage, and one extremely nice thing about MicroK8s is also that it comes with some add-on. So just with adding these add-on to the MicroK8s with the first command, we can actually already deploy and have a Mini.io deployment on our local environment. We can configure, of course, we can get like the access key, the secret key, and the endpoint, and we can configure a CLI, a client CLI, with this credential that we can also use to just create a simple bucket that, as you will see in the following, we are going to store our data into this bucket. And finally, we are going to use Juju. So Juju is actually an open source orchestration engine. So basically what Juju will allow us to do is to basically deploy and manage all the different products, all the different platforms that we are going to deploy in an extremely easy way. So basically within Juju is going to orchestrate the entire process from deployment to managing. And we are going actually to use what are called charms, that they are basically the software operators that they are going to manage the platform themselves. So one of the things that we have to do is actually to set up the environment, we have to just deploy a controller, which is actually the orchestrator that is going to take care of managing and integrating all the different applications. So by using Juju, you will see in a moment that we are going to deploy a Kafka cluster alongside with Zookeeper. Zookeeper is basically a controller plane for Kafka. And we are also going to also deploy a producer application, which is just producing a number of messages to the Kafka cluster. So this is what we're going to do in the next video. So actually, like Juju can also work with YAML. So here you see that there is a YAML that we can just where we can configure the deployment. So with a Kafka cluster, with a Zookeeper, and with a producer application. So by just doing Juju deploy, you'll see that we will get now a cluster, like the application that they are up and running, as you can see from the left-hand side. And at this point, we can just actually create a relation between Kafka and the producer application. And as you can see, we will actually be already starting to produce some messages to the Kafka cluster. So with extremely like a few commands, we have already deployed a Kafka cluster alongside with Zookeeper, and also like a producer application, which is already producing some messages. So the next sorry. Okay, the next step is now to deploy a Spark streaming application. So as Rob said, a Spark application is composed of a driver program and some worker and some workers, which basically are the one processing the data, ingesting the data, and processing the data. Now in Kubernetes, all of these they run as pods, and of course we have to set up a service account to run these pods. Actually, as part of the tooling that we provide with Charm Spark, we also provide a way to actually set up this service account and also configure this service account to run on Kubernetes with a snap. So we provide we have developed a snap which basically allows people to just set up a service account and also configure. So provide some central configuration that is the Spark jobs they can run with. And the way it is going to work, I'm just going to show how this Spark client utility works. You see that we have a Kubernetes cluster. We just create a Spark namespace. And for instance, we can use the service account utility to first list, but also to create a Spark service account. So as you can see, now we have a service account, as well as we also have some secrets where the different configuration for the Spark jobs are going to be stored. As you can see, indeed, we have now this new service account, and we can also retrieve the configuration. Now the configuration are going to be extremely simple because we haven't added any configuration yet. You will see in a moment that we are going to do this. So with this service account, we can, for instance, start a PySpark shell. So a PySpark shell is basically an interactive shell in Python that allows you to run Spark jobs. In fact, as you can see, we already have a couple of executors that has been spawned as soon as the Spark shell was started. And we can just perform some very simple operation. This operation is to be noted that they are going to be run on those executors. Another way to actually run Spark jobs is also to submit Spark jobs. So as you can see now, we are going to submit a very simple Spark job that is going to basically do a Monte Carlo simulation for evaluating the pi number. So one way to do it is actually to do Monte Carlo simulation to get an estimation for this number. And we have already created this simple job. And as you can see, when we start this job, there will be a driver, which is actually running the main program, as well as the executor. And if now we go into the logs of the driver, you'll see that we'll have the result of the computation right there. And we have started all these processes using these Spark clients now. Now we're going to actually customize a little bit this Spark job. So for instance, we are going to increase the number of executor. And one can just use, once again, this utility to add some configurations to the Spark to the Spark service account that we have created. As you can see, now we have injected this configuration. And if we run again the job, you'll see that at this point we will have actually 4 executors running instead of just 2. Of course, as you can see, finally, last but not least, we can also remove the Spark service account just using this CLI. All right, so with this CLI tool, one can indeed actually work on. One can actually set up the configuration, the Chance Spark service account. However, one easy way to do this is also to using the so-called integration hub, which also shows how the Juju ecosystem works. Because with the integration hub, just using relation, so relating different components, we can actually from one side set up, configure the configuration in a high-level way. So, for instance, by just integrating with S3 or an observability bundle, we can just generate all the set of configuration needed to have these functionalities. And on the other side, we can actually relate the integration hub to client application to actually configure the service account for those client applications with basically no requirement for actually put in all the commands as we did before. Everything will be done using Juju by just relating to components. So what we are going to do now, we are going to deploy a streaming application, which basically just, of course, instantiate a Spark session. Then it reads data from Kafka, and then it performs a near real-time aggregation. So we are just going to group by all the messages by the origin and the time and the window, the timestamp, a window timestamp of 10 seconds. And finally, we are going to write this to a Hive table. Now, Hive table is, we're going to use Spark SQL for doing this. And a Hive table is composed by 2 building blocks. One is the data catalog, so where we are going to store information about the structure of the data. And this can be implemented, as also Rob said, by the Hive metastore of Postgres. We are going to use Postgres, as we discussed before, and also the raw data. The raw data, on the other hand, they are going straight to an object data storage, in this case, as we said, Minion. So that's what we are going to do. We are going to deploy all these building blocks, once again, using Juju. So, first of all, of course, we deploy the Spark streaming application, once again, which has been charmed. And as you can see, as soon as the Spark streaming application will come up and it will be active, it will be into a block status because it requires to run a Spark service account. You see that it says that we need to relate it with an integration hub. So that's what we are going to do. So we are going to deploy the integration hub, the metastore with Postgres, and the S3 integrator. Basically, the S3 integrator will bind to an existing S3 backend. As you can see, we already have the Minio endpoint where we have created, as we said before, the Spark demo bucket. So we're going to deploy this the bundle, and you will see that after a few minutes, everything will be into block status because we have to feed the credential. So we're going to feed the credential, and now we have everything which is in an active state. At this point, we can indeed actually relate our consumer application, the Spark Streaming app, to the integration hub. So we're going to create this relation, as well as relating also with the Metastore and with the Kafka, because we want to consume data from Kafka. At this point, the apps, they are all active. So, and indeed, after the relation with the integration hub, you can say that now we have a Spark service account with basically with all the configuration about Minio already injected. At this point, we can just actually run our process. So we can, with an action, we can just start the process, and you will see that as soon as we start the process, we will start to have the two executors on Kubernetes that they are taking care of basically consuming data from Kafka, doing the real-time aggregation, and then writing this data into S3. And indeed, we can actually check that in the S3 bucket, we have some data. So the data is under the folder warehouse. Relation 10 is the name of the table. And as you can see that here, we have a bunch of Parquet file where the data is being stored. The next step is to deploy Kubi. As Rob said, Kubi works with a Spark SQL engine to perform the queries. So also for Kubi, we will need to basically have a relation with the integration apps that will basically take care of creating a service account. So first of all, we deploy Kubi. And also, as I said, in this case, you'll see that the charm will go into a block status, asking for a relation with the integration hub. So we go ahead and we create this relation alongside also with the relation with the Metastore, from which Kubi will retrieve the information about the data catalog. At this point, we are pretty much done. So we can just list the service account and check that indeed a service account has been created. And we can, and we just need to wait a few seconds for all the charts to settle down. And we can now retrieve both the password and the JDBC endpoint that Kubi provides. So we can also use a command line tool, which is called beeline, to actually get access both for basically to get access to connect to this JDBC endpoint. And as you can see, as soon as we start the connection to the JDBC endpoint, we start both a driver and the executor where the queries will be run. You can see that now we can use SQL queries to, for instance, just show all the tables. We can connect to this endpoint also actually using some graphical user interface. So in this case, we're using the Beaver, and once again, we can just plug in all the credentials, so username, password, and also in this case, you'll see that in a show while we will have we will be connected to the database, so we will be able to explore the data catalog. We will also be able to perform queries. Like using standard SQL dialect. And there you go. So you have actually this result that they are the real-time aggregation.
We're going to have to stop it here, I think, because we're running out of time. So okay. So we have more to show, but unfortunately we've reached the top of our allocated time. So thank you very, very much for attending our talk. It's very much appreciated. Take care and see you in the next one.